Assalamualaikum and greetings to all of you. Today, our topic is still going to be about the principle of energy and thermodynamics, but we're going to focus a little bit more on the thermal part of it. So here, this is part 3. Yeah. Basically, today's learning outcomes, there are two, to understand the law of thermodynamics in the context of energy, and secondly, to describe entropy and energy change. Okay. But before we go any further, okay, my advice to you would be so that you would understand the definitions of the of this listed item. Now, word energy principle, what it is actually. Okay, we have look at what exactly is counted as work in the previous lecture, and what is heat. Okay, it's the transfer of energy, okay, and that is the equation for that. And at the same time, if you guys still remember, we did talk about internal energy in terms of thermal energy. Remember the things where it's vibrating, the atoms is vibrating. So you can actually calculate the internal energy through this equation. Okay, but also take note of this one, work energy principle. So work is W, Q is heat, U is internal energy. Okay, and we actually have, we touched upon this in the part 1 lecture on this topic about the conservation of energy. So remember, a total energy, E, is the sum of the energies. It is logical. We're talking about total energy, right? So it's the sum. Okay, so any energy that is available in a system, okay, you can be sure that the amount will be conserved. So whatever is going in, okay, and whatever is going out, it's going to be similar, right? Now, so here, conservation of energy. So total energy E equals to K plus UG plus US plus UChem plus EChem plus E thermal. So I'm positively sure that you guys can remember, okay, what are these notations here. Okay, bear that in mind as well, right? And we also have kinetic energy. The kinetic energy can be calculated using this equation. So all of this, 5 of these equations, really, really important, especially when we talk about energy, right? Because it's all interrelated, okay? Especially if you want to talk about a system. Okay? If you still remember in our previous lecture, we talk about open system versus closed system versus an isolated system. Okay, so let me just draw that for a bit. Okay, open, closed, and isolated. So imagine whatever system this is applicable. That if there is anything that can go in and go out, it's an open system in terms of mass. Okay, but here the mass cannot enter or get out, right? However, energy can still move in or out. And that is completely different when we talk about isolated system, in which there is no exchange, mass or either energy exchange from the system to the environment. Okay, so anything that is happening inside a system, okay, it doesn't matter what system it is. Okay, let's imagine that is a system. Okay. The total energy here inside the system, okay, is going to be be determined by all of this. It's possible that one of them will not be there. Okay, so you will be able to manipulate this equation based on the situation, based on what is truly happening, so on and so forth, right? So just bear that in mind. Now, we go into thermodynamics. So what exactly is thermodynamics? So it's actually one definition. So this is not the overall definition, it's one of it, but it's talking about the study of the general properties of energy. It's quite general if you think about it. General properties of energy, again. Okay? And we have three laws usually, but then even when I was in high school, I learned about this one. First law, second law, and third law of thermodynamics, right? But basically, if we talk about thermodynamics, there are three major elements. First is the principles, which is all of these three, okay? Principles here. And then the properties, okay, properties of the whatever elements that we're talking about. Okay, maybe it's a gas, is it ideal gas, is it non-ideal gas, so on and so forth. Okay, so that's gonna, they have different elements to it, basically. And lastly is the processes. Okay, it's, any process. Is it a fast process because it's non-equilibrium? Okay, is it an equilibrium process? All of this are what is included when we talk about thermodynamics. However, today we're not going to go too deep. Okay, this is not chemistry and this is not physics either. Okay, we are talking about energy. So my approach is for you guys to understand when we talk about first, second, and third law, what exactly is it related to energy? Okay, so even here you can see first law, energy, work, heat. That's what we've learned before, okay, which is why the previous three lectures was on principles of energy and thermodynamics. Okay, so because this is all talking about first law. Okay, we also have entropy as a second law, right? And we're going to look as well on to the third law. However, there's another one. Okay, there's something called zeroth law. Okay, this actually comes after the three laws were established. Okay, and it's something that is quite straightforward. Now you think about it now, but back then it was something that people were like thinking about, but they couldn't find it in the first three law. Okay, however, this fundamental thing is so important. It's governing all three other laws. That's why they don't put it as the fourth law of thermodynamics, but they named it as zeroth law. Okay, meaning that it should comes first. Yeah. Okay. Now, what is zeroth law? Zeroth law is actually, so we're going to look into the first, second, and third as well. Okay, but for now, we are going to focus more on the zeroth law. Okay, and just to see what is it talking about. Okay, so zeroth law says that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other, and there is no net exchange of thermal energy between them. Okay, and this is actually what gives us the concept of temperature. You remember before the previous lecture, okay, I was talking about what is temperature. Okay, and if you guys still remember, I hope you still can. Okay, temperature is the measure of the kinetic energy. So if not, it's different than if you measure length, for example. You have a ruler. Okay, you have a ruler. Okay, and this is the equipment to measure length. Okay, you want to measure the length of something. But if you have thermometer, okay, it is still a device to measure the temperature, However, temperature itself is not something tangible. It's not something like length. Okay, so before Zeroth law, there wasn't any idea about temperature. I mean, in terms of measuring it. Okay, because without the concept of this concept, the thermal equilibrium between different systems, you won't be able to measure actually. Because why? Remember before when we talk about measuring the specific heat of something, and we use the calorimeter. Yeah, remember how it is in an isolated system, and you have it's a closed system, and you have a temperature, you have a thermometer, okay? And basically, you use the equation, okay, to know, okay, the difference in temperature, okay, will lead you to calculate C, which is a specific heat. Okay, but there is no way for you to just measure temperature on its own. It's different for us now. You think about it. We correlate already 0 degrees Celsius with ice, for example, the freezing point of water. And we denote 100 degrees Celsius to things that are boiling. Water is boiling, it's 100, and freezing at 0. So that is, to us, okay, now it's common. Okay. However, can you just touch something and you know that this is 37.7 degrees Celsius? Or you touch a lamp and you say, oh, this is 80 degrees Celsius. Not possible. Okay, because there is no way to measure temperature. Okay, so with Zeroth law, it allows us to say like, hey, okay, we have this system. Look at this one, thermometer, right? So thermometer is a system. It's a closed system, okay, because you have all of this is in one enclosed compartment. Okay, you have the alcohol here, and the expansion of the alcohol will relate to the temperature. Okay, just bear with me. So that is one system. Okay, so imagine you are you have a fever. Okay, and you're testing your temperature using a thermometer. You put it under your tongue. Okay, and this one will expand until it reaches a point where it achieves equilibrium, okay, with the temperature of your body. So this is what Zeroth law says. So if these two, okay, the thermometer and your body reach a thermal equilibrium, okay, then you can say like, okay, these two has the similar thermal energy. Okay, so you can say that the temperature is similar. Okay, so that is the concept of Zeroth law. Okay. Now, knowing how much energy the two systems have does not let us predict which direction heat will flow if both are in contact with each other. Okay. So the Zeroth law says that this number, the temperature just now, it defines the direction of heat flow, okay, which does not depend directly on the amount of energy that is involved. Right? That's what Zeroth law is saying as well. Okay. Now, so of course, if we're talking about things like this, right? So thermometer, just now we're talking about the expansion of alcohol, okay, until it reaches the equilibrium with our body. Yeah. So this is where calibration is really, really important, you know, because there is a situation where if the calibration is not right, then you won't be able to get, you know, it's in equilibrium, but maybe the reading is different. Okay, so just throwing that out there, no worries about that. Okay, and lastly here, zero temperature. Like I mentioned before, is it possible to have 0 Kelvin? Sorry, no degree there. 0 Kelvin. Okay, 0 Kelvin means it's absolute zero. And remember, it's something that is not found in nature. Okay, it's the condition where there is zero internal energy in the atoms. Yes, no matter how low, how cold you went down, yeah, you won't be able to get to a point where there is no movement at all in terms of the atomic level. It's not something possible, but we still have this concept of absolute zero to give us an idea, okay, of the very maximum or the very minimum level temperature can go to. All right. So temperature scale, just throwing this out there. I'm sure you guys can look it up as well. Fahrenheit, Celsius, and Kelvin are interrelated, so you can use them based on, you know, these correlations. So yeah, so I've mentioned this as well here, so you guys can always remember that. Yeah, but always remember, especially when you're doing calculations, when you're trying to use equation, you have to be careful of the units. You have to know which units you are using, which units that particular equation requires, and you cannot just interchange it. Okay? So if the equation calls for Kelvin, and you were given the reading in Celsius, then you have to change it, right? Now, done with zeroth law, we go now into the first law of thermodynamics. So the first law of thermodynamics, it is actually a broad statement of the conservation of energy. Yeah, we've looked at it previously. So we can say that in a system, okay, delta U, okay, sum total of all energy of molecules of a system is equals to Q minus W. So it means that whatever is left internally, okay, is coming from the heat flow in or out of the system minus the work done by or on a system. Okay, so take note of the slash here, because it's going to really, sometimes people get confused, okay, because this will denote whether this value is negative or positive, and here as well. So flow in and flow out, okay, positive and negative, and work done by and on a system, okay, is negative and positive. Okay. So by general definition, the first law says the change in the internal energy of a closed system is equal to the energy added to the system by heating minus the work done by the system on the surrounding. Okay, so exactly, if you can remember this, yeah, you can definitely define what is the first law of thermodynamics. So here as well, so you see this one. So it totally depends on whether, okay, here it makes it easier for you. Plus Q is heat added to the system. Okay. Negative Q is heat leaves the system. Plus W is work done on the system. And negative W is work done by the system. Right? So it's always, we're always looking at the system basically. If you expend energy, yeah, if you expend energy lah, basically, you are doing some work. That system, I mean, is doing work. So it means you lose something. Yeah, you lose work. I mean, negative W lah. And also the heat leaves the system. You are losing something. So it's always negative. However, if you're gaining something, then you got heat added, it's positive, and work is done on the system, okay, it's positive. That's a way for you to remember it more easily. Okay, so it's actually an extension of the first law for a moving system. Okay, we can actually expand this into that. So any changes in internal energy is equals to any changes in the kinetic energy plus changes in the potential energy. Okay, and you will actually get the same. Right? So remember the 5 equations that I mentioned earlier. This is where you have to use it. Okay, and also, if we're talking about gas, the work and ideal gas is interrelated. So you know this equation already, W equals to FT. Okay, and you know this is pressure. The pressure is force divided by area. Okay, and you can actually correlate that until you get this equation. Okay, it means that the work is equal to negative P delta V. Okay, V is the volume, right? And if you guys still remember, in chemistry, we have PV diagram. Okay, so in PV diagram, it's actually possible for you to calculate W. Okay, if you know any of this, yeah, the two. And you can actually calculate W from the PV diagram. You just need to know what is the initial state, okay, and what is the final state. Is it going here, going there, or here? Okay, that will help you. So as an example, okay, the thermodynamics process lah. Yeah, so this is the basic chemistry. Okay. So consider a system of an enclosed cylinder filled with ideal gas and with a movable piston. Okay, imagine that the piston can move up and down, right? So it can move, okay. However, it cannot leave anything that is inside. It cannot leave the system. So it's a closed system. However, remember, in closed system, energy can still go in or out. Okay? And just imagine that around it is a heat reservoir. Okay? And this is an infinitely large heat reservoir with no significant change in temperature. Okay? And bear in mind this equation, delta U equals to Q minus W. Okay? So consider when heat flows into the system, okay, you know that there's heat here, heat reservoir, so it goes in here. So what happens to the gas when you heat it up? It's what happens to everything else. Right? If it's solid, you know, if we're talking about steel, you can actually see that happening. If you heat it up, it's going to expand. Exactly what is happening with gas. You heat it up, the gas is going to expand. And when that happens, remember the piston is free to move, so it's going to move up. Okay, and what happens there is the volume will increase. Okay, therefore, in this kind of situation, the work is negative. The work is negative because it is done by the system. Right? It's expanding, so it's pushing the piston. So that means the work done is negative. Yeah. On the other hand, if heat leaves the system, okay, just imagine that it's the other way around. Okay, so it leaves the system, this will start compressing. So as it compresses, the volume will decrease. Okay, and the negative of this and the negative of that will cancel each other out, and you will get a positive number. Okay? You calculate that and you will get a positive number. So that means that work is positive. Okay, it is done on the system. All right. Okay. Now remember just now I was telling you that we can calculate work through the PV diagram. Okay, so this is another equation, one of the 5 equations that I mentioned before, PV equals to nRT. And this is ideal gas equation. I hope you guys can still remember. Okay, if we correlate the two, we can actually get, W. Okay, you can actually calculate it using this. Yeah. So basically, if we graphically graph this, for lack of better terms, okay, you can get this diagram. Okay, and this changes, it means that the area underneath this is the work. Okay, hope you are still with me. So remember, just now, in state 1, okay, the piston is here. Piston is there. Okay, that's state 1. And as the heat leaves, okay, the piston will move down, the volume will decrease, okay, and you will go to the second state. Okay, so imagine this is the first state, okay, and you're gonna have V is reducing, right? So it's definitely going that way, right? And pressure here, okay. So it goes up, and you can actually calculate W by measuring the area underneath that. Okay, so this is easy if you have a graph paper. Yeah, and this is how I do it. I still remember I calculate things like this in SPM. Yeah, we do this in the graph paper. But basically what I'm saying is that this is how you can calculate W if you are given a situation like this, right? Now, we'll look further into that, but first we go into some examples. Okay. So number 1, 5,000 joules of heat is added to a closed system, which then does 3,000 joules of work. What is the net change in the internal energy of the system? Okay, it's very easy because you know this equation already. Okay, so 5,000, yeah, minus 3,000, easy. You got 2,000 joules. Yeah. Now, secondly, a liquid is changed to a gas at atmospheric pressure. The volume of the liquid was 5 times 10 to the power of negative 6. The volume of gas is 5 times 10 to the power of negative 3 meter cubic. Sorry, how much work was done in the process. So if you know the P here, yeah, and you know the volume, you will be able to calculate that. And you got this one. You just be careful about the notations. Yeah, is it positive or is it negative? Okay, and look further here as well if you see something. Yeah. Now, in PV diagram, okay, I'm not gonna go too deep into this one. I'm sure you guys can read it up. I've attached the lecture note in PB as well, so you can definitely go back and read this. Yeah. So just remember about what is certain processes called as. Okay, isobaric, we have isovolumetric, we have isothermal, and we have adiabatic process. That's 4. And that correlates actually to what is happening in the PV diagram. Yeah. So if you are given a situation, yeah, the easiest thing for me, what helps me was to try and graphically imagine it. You can always do that on paper as well, because you can actually see where things are going, which is state 1, which is state 2. If you're asked to calculate work, then you can definitely work on that easily, rather than just looking at it on your own, right? So each of these processes, okay, corresponds to different, we can say that this is cheating a bit lah, because we know, like, for example, isobaric process A to B. So W equals to P negative delta V is not equal to 0. Okay, and you will get, you will need to calculate lah, basically. Delta U equals to Q minus P delta V. Yeah. But it's different if it's A to C, which is isovolumetric, meaning that isovolume, similar volume. When it's similar volume, V is 0. So you know we have W equals to P delta V. If this is 0, then this is 0 as well. Okay, and you can actually get delta U as Q. Okay, so that's how we can ease a bit lah, how we can remember. Yeah, but it depends on whether you truly understand, okay, or if you just look at it and you have to really think about it. Okay, and this one as well, yeah, it's summarizing the processes and what is constant, right? Now, in PV diagram, okay, what happens to work done and internal energy as the gas expands, right? And exactly the same, what happens when the gas compresses. Okay, so basically this is just for you to understand more about the sign. Sign here meaning positive or negative sign. Okay. For example, here, if the gas is compressed, volume must decrease and work done is positive. Yeah, sorry, if the gas is compressed lah. If the gas expands, volume increase and work done is negative. Okay. And this is very, very important, especially when you have that equation and you have to think about when is it negative, when is it positive. So this is very, very helpful in terms of that. Okay. And then sign of internal energy is proportional. So if PV increases, then P and U also increases. Okay, so that's how we can actually predict whether it's going to be negative or positive, right? Now, that is about the first law of thermodynamics. Now we go into the second law of thermodynamics. And basically, second law is about entropy. Okay, so before we go into that, just bear with me here. The first law of thermodynamics tells us that during any process, energy must be conserved. That is something you know already. Okay. However, it doesn't tell you the direction. Okay. If it's a process, it doesn't tell you whether it's going forward. And if you still remember chemical processes, is it going forward or is it reverse? Yeah. And what process will happen spontaneously. So the easiest depiction of this is, does this happen in real life? So initial state is something that is like this. The cup is broken. Okay. And second stage, it's like it reassembles. Okay, the ones that was broken just now, the pieces reassembles themselves and rises up, right? And final state is that it lands on the table, just nice like that, one whole cup. Okay, it doesn't happen in real life. Okay, but if only based on first law, okay, this situation above is not contradicted. It's not saying about the direction. Okay, but we know that some processes can only happen spontaneously in one direction. This one, instead of like this, it's only possible this way to be done spontaneously. Okay, it's something on the table, you push it down, it goes down and breaks. It breaks apart. That is what is happening in real life. This one doesn't happen. So that means that there's another law that comes after this that tells you in which direction a process will proceed spontaneously. Okay, similar thing lah. If you have in the same vein, you go home, and you rest. You know, this is like apa tongkang pecah orang cakap. Okay, a lot of mess everywhere, and suddenly 5 minutes without you doing anything, and no one is helping you, things go back to where it was. I cakap dah hantu pula. No, this doesn't happen. It happens the other way around. Okay, from something that is neat going into something that is messy. Okay, that's always the direction it's going. That is exactly what entropy is. Okay, so the second law of thermodynamics is a statement about which processes occur and which do not. There are many ways to state the second law. Here is one. Okay. Heat can flow spontaneously from a hot object to a cold object. It will not flow spontaneously from a cold object to a hot object. Okay. And this is natural. Yeah, we know that already. Okay. Everything that is hotter, it will flow into a colder place or colder object. Yeah. And for example, your fridge, there is something there that helps it to keep it cold. Otherwise, it's going to get warm spontaneously. And that happens, you see, when there's no electricity for 7 days, for example. And your fridge is going to get hotter and hotter. The ice will melt, so on and so forth. Because there's nothing that helps it from keeping cold. Okay, this is the second law of thermodynamics. And remember just now when I talk about something that is from neat to messy, okay, that is entropy. Entropy is basically saying that it's a state of order to a state of disorder. Okay, and entropy itself is a measure of the disorder of a system. Yeah? And just like your room just now, just like the cup, natural processes tend to move towards a state of greater disorder. Daripada something yang neat, something that is assembled nicely, it will go into a position that is more disordered, it's more messy. That's in nature. Okay. So another example, if you put milk and sugar in your coffee and stir it, you wind up with coffee that is uniformly milky and sweet. Okay. However, can you reverse that process? Can you keep on stirring and then suddenly milk and sugar come out? Not possible, kan? That's not natural. Okay, so the natural system will always go out of order. All right, and thermal equilibrium is similar. The uniform final state has more disorder than the separate temperatures in the initial state. Okay, this is talking about entropy. Now, if we relate that to the heat engine, okay, just remember, if you don't know what heat engine is, just bear with me. So basically, it is easy to produce thermal energy using work, but how does one produce work using thermal energy? Because like simple thing lah, produce thermal energy using work, always kalau you kayuh basikal, there's always going to be heat, you know, gave off. You feel hot, so on and so forth. But how do you produce work using thermal energy? From the heat difference, how can you produce work? So that is where heat engine comes in. Heat engine is the device that changes thermal energy into mechanical work. Okay? And the mechanical energy can be obtained from thermal energy only when heat can flow from a higher temperature to a lower temperature. Okay, imagine there's an engine here. Like I mentioned before with your fridge, okay, outside is at a higher temperature and your fridge is at a lower temperature, okay, and the heat difference, okay, allows the heat engine to work, okay, and it changes these thermal differences, okay, the difference in temperature into mechanical work, okay, and imagine it's an engine, so you use the thermal difference, okay, to move something, right? So the analogy is it's almost similar to something like this. Okay, you have this is talking about potential energy lah. Okay, but if we're talking about heat engine, it's a similar concept. So you have water at a higher elevation and you have a water wheel. Okay, as the water flows, the wheel will turn. Okay, and actually this water flows from a high energy point to a lower energy point, and because it's at a lower elevation, okay, and as it goes down, it will help the wheel to turn, okay, and as something is turned, that is called mechanical work. Okay, of course here it seems like something general, right? But you can actually imagine if it's connected to something like a generator, you can produce electricity from this process. Yeah, and that's basically how electricity is produced as well in power plant, in windmills. You have wind turbines, right? So that's how it works as well. Something is turning and it's connected to a generator, okay, and that generator will create the electricity from the mechanical energy, right? So it's bear that in mind and try to change from water to something like heat. Right? It's going from higher elevation to a lower elevation and it's turning something, creating mechanical work. That is a heat engine. Right? So we have engines that run in a repeating cycle. Okay, and the change in internal energy over a cycle is zero as the system returns to its initial state. The useful heat engine runs in a repeating cycle. So you're going to have this one. Okay, so over a period of time, okay, the change in internal energy is zero. Okay, so you will be able to actually calculate QH equals to W plus QL. Okay, and you can relate that here as well. So you can actually calculate W. Okay, and if you know what is the temperature here, then you can definitely know what is the work that is being produced. Okay, so this is an actual representation. Just now we talk about heat engine is actually an idea. Okay, it's the concept. Okay, but what can be gained from real life is steam engine. Okay, so in steam engine, it's basically you have your steam. Okay, you see boiler here. So you have water. Water is heated up and it changes into water vapor. Okay, and that is steam. Steam goes into the engine. Okay, and remember just now, as heat goes into a system, it expands. Okay, and as it expands, this is going to move. Right? It's going to move like that. So this is what's happening in almost similar lah, but not exactly the same. But if we're talking about your car, okay, unless you're using an electric car, okay, the fuel car uses something similar. That's why you have piston in your car. Okay? So as the gas expands, Okay, this will move forward, create work, and this is going to move. Okay, and the piston is going to transfer this mechanical energy into the mechanical work that is moving your car, okay, towards your tires, okay, and changes to, it goes to your actuator, okay, to change that into electrical energy for all the electronics in your car, so on and so forth. So there's a lot of energy generation inside the car system, and this is the basic of it. Yeah, the piston. Of course, this is steam engine lah, but it's all almost similar. So anyway, as this goes there, and as it's expanded, it goes back to its initial condition. Okay, the steam moves then into the condenser. The condenser will condense that steam into water again, and the pump will pump this back into boiler. And this is a continuous process. It's always going to generate power here. Okay, basically the mechanical work. Right? Now, so this is what I mentioned before. So internal combustion engine, this is your car, okay? The fuel car lah. Doesn't matter if it's diesel or if it's petrol. Okay, you're always going to use internal combustion engine. So it is a type of heat engine as well. Yeah, and see here, this is a crankshaft. Okay, and if you know your car, you have spark plugs. Spark plugs here is actually creating the spark, and you know, fuel goes in. So I'll just gonna go through with you the basics of this. The fuel goes in. Okay, petrol, for example, goes here, and then as it is heated up, yeah, with the spark plug, it's gonna combust. Okay, and as it combusts, this will turn. So you notice the movement of the crank here. And as that movement happens, this is happening really, really fast. Okay, really, really fast. So you can imagine how much energy is being generated, okay, in your car to keep it moving, to keep it, to have enough energy for the total requirement of the car. So now, just quickly about this lah, the efficiency of heat engines. So it's actually E, it is the ratio of the work done to the heat input. So W over QH, right? And if we use the conservation of energy to eliminate W, we can actually get this one. So E equals to 1 minus QL over QH. Okay, QL, QH, I'm sure you can still remember, similar to here. Okay, so if you can imagine this in your mind, or you can just write them or draw them on a piece of paper, that will help you a lot. Okay. Now, this is Carnot engine, so I'm not going to go further into this one because it's an additional information lah. But it's actually, it is idealized because it has no friction. Okay, and you can actually look at how, you know, remember just now the 4 processes: adiabatic, isothermal, well, these 4, you can actually look at that physically using the Carnot engine, but it's not used in practice. Okay, so the efficiency of heat engine, okay, for an ideal reversible engine, the efficiency can be written in terms of the temperature. Okay, just now, if you still remember, it's Y minus QL over QH. But for Carnot engines, because this is ideal, okay, you can actually calculate that directly using temperature. Okay, so don't worry, guys, this is not about calculation. I just want to highlight from this here, we see that 100% efficiency can be achieved only if the coal reservoir is at absolute 0. okay? Because only if you can get 1 E as 1, okay, if this one is 0. Okay, this one cannot be 0 lah, then it becomes infinity. So this one is 0, so 0 minus something becomes 0. So 1 minus 0 is 1. Okay, 100 efficiency can only be achieved if this is 0 and this is similar as absolute 0. And remember before when we talk about zeroth law, it is impossible. So from this, okay, we can conclude, okay, that real engines, okay, have some losses. It's not possible to get 100% efficiency. And because it has frictional losses, there's also heat loss, for example. Okay, so the best achieved efficiency is around 60 to 80%. All right. So entropy, again, and how it relates to the second law of thermodynamics, okay, we can actually calculate delta S, which is this change in entropy. Okay. And that is through this one. Delta S equals to Q minus T. Okay. So this brings us to another statement of the second law of thermodynamics. The total entropy of an isolated system never decreases. It is always going to be higher. Because always remember that entropy basically, because we are talking about natural system as well, it's not ever going to be reversible. Just like your room, just like the cup just now. Okay, so correlate the heat engine to what is around you. You have your refrigerators, you have air cons, you have heat pumps. So these appliances is actually heat engines. Right? Remember, I told you before, heat engines is a concept. Okay, so these appliances is actually heat engines in reverse. So instead of you trying to move, okay, instead of the heat moving from hotter condition into colder situation, it's the other way around. Okay, so instead of generating work, you give work, okay, to the system. Okay, and in that situation, you will be able to extract heat from your fridge into the hot reservoir, so into your surrounding. And this is the work is required, and that is where the electricity comes from. Okay, so you need electricity to run your air cons, to run your refrigerators, and this is how it works. Okay. Of course, this is just a representation, so you are familiar with this one already. Okay, and this is what's happening actually inside the refrigerator. Okay, you will have your heat sink. Okay, this is actually your motor or your compressor. Okay, it's going to, you are giving it energy for it to work to extract heat from your fridge into outside. Yeah, so it can be fridge, it can be aircon lah. So this is what's happening. Okay. So even with refrigerators, aircons, and heat pumps, you can actually measure the performance using the coefficient of performance. This is similar as before, but it's only using denoting different words. So my point here is that if you understand how these are calculated, and basically if you know from the conservation of energy, you can actually calculate a lot of things, and you can manipulate a lot of things. So it doesn't matter even if you did not remember like specific equations like this, because you already know. Okay. So So lastly, this is about heat pumps. So with heat pumps, this is usually at colder climate countries, where it's in winter, for example, okay, and the house, you want it to get warm. So you use heat pump, okay, to actually get heat from outside and enable your house to get warmer. Okay, you have your heat pump over there. But of course, this is also doing work, okay, needs electricity, always similar. Okay? So why delta T is needed to get W? Okay? That's the reason why. Okay, because we need the temperature difference, because it's going from the hot condition to lower condition. So if you want something generated, you want energy, you want electricity, for example, you want mechanical work from this process, it's always going to move from hot to low temperature. So always going to need a situation where, if you have this steam engine, always going to have two compartments, the boiler and the condenser, because these are the things that will enable whatever solution, whatever, this is water, right? So this will keep it hot and this will keep it cold, okay? Because you need the temperature difference, right? And only then will you be able to generate the mechanical work, all right? So, all right. So lastly, this is just going a little bit into thermal pollution, global warming, and energy resources. Okay, the generation of electricity often involves a form of heat engine, whether it is powered by biomass or solar power. Okay, and cooling towers are a feature of many power plants. So basically, even the most obvious impact of electricity generation, you can see from the carbon emission. Okay? But at the same time, there's also thermal pollution as well, okay? Because you're always going to have an excess of heat that you need to cool down, which is why we have cooling towers in lots of these power plants. Yeah. So also, this will also, other than the carbon emission, the thermal pollution is also a factor that leads to global warming. Okay. All right, so this one is actually something to relate to that lah. So you can actually correlate that to a specific number, okay, QL, basically because that is the heat output of your heat engine. Okay. And remember just now when I talk about your refrigerator and your aircon, you are actually moving the heat, okay, from something that is actually cold into the environment. So this means that, okay, if we look at it as an outsider's point of view, okay, you are actually, this heat actually has to be absorbed by the environment. Yeah, and as the world gets hotter and hotter, we use more and more aircon. Yeah, can you imagine what is happening as well? Okay, so the heat is not only coming from up there, it's not only coming from the greenhouse effect. Yeah, it's also generated by human activities as well. Okay, this is why we have to be reflective of whatever that we are doing, whatever processes, whatever equipment that we're using, okay, everything has its own cost to the environment. Okay. So, of course, another one is air pollution. Air pollution, the build-up of CO2, and now people are going into more and more environmentally friendly options. Okay, however, we still cannot escape from the situation where carbon is released and heat is released to the environment, but we can try to reduce it. Yeah, I hope you guys know about even Malaysia's aspiration. Yeah, we aspire to be to reach 40% of reduction in carbon emission compared to 2005 levels. Okay. And this is all related to this. We need to take care of our Earth. Okay. Climate change has to be stopped and it has to be reduced. Not possible now to stop it, yeah, but you can slow it down and you can keep it at a level where it's acceptable. You can adapt to it. So this one as well, I'm just putting this here to talk about a little bit about the world. We look in specific equipments, but at the same time, if we look outward, the Earth itself is a heat engine. Okay, why? Because if you think about it, the most coldest point, like here, the polar, it's cold, right? And we have these areas which are hotter, and we know that heat is going to move from the hot place to the colder place, yeah, and that is actually what generates this wind, the wind system of the world. We have northeasterly, we have the southeasterly. So these are actually what a lot of our climate is depending on this process, this natural process. A lot of things is related, is interrelated, which is why our activities, the human activities that is leading into climate change, yeah, it's really, really something that we have to reduce, because it's not only affecting us, it's affecting the whole world. So the example is this one. Just now we talk about the northeasterly and southwesterly, but we also have this thing called sea breeze and land breeze. Because what happened is that water, yeah, it heats up less, how do we say it? It heats up slower compared to land. Okay, so in the mornings, usually the wind, yeah, will move. Okay. This will relate to the atmospheric circulation. Okay. And at night, yeah, because water now it's slower to heat up, but it's also slower to release the heat. So at night here, the water is warmer compared to the land. And that will then generate the wind in the opposite direction. Yeah. So this is what helps our climate as well. And on a large continental scale, this is also called the monsoon circulation. So that's it from me. I hope you guys are still okay. And I will see you next time, okay, in our next lecture. Right? Thank you. Bye.